Swayam Prabha. Digital India. Educated India.
Welcome back to the second week of Bioelectrochemistry. So, in the previous week, we are supposed to finish all the way up to Nernst equation and electrode potentials. We could not really reach there because I was concentrating exclusively on the fundamentals. So, we will have a little spillover this week, which will continue, will be slightly delayed, but kindly do not worry. We will compensate it, may have extra lectures, or eventually we will kind of make up for the delay what is happening at this stage. But what is most essential is your fundamentals should get very clear at this stage, because once we will be talking about the biological systems, they are far more complex than these inorganic salts and inorganic solutions. So, that is why I am devoting all my time at this stage to clarify all the doubts. So, just a small recap, when we talked about in the last class about the galvanic cells, we put up a definition there which I wanted to again revisit. So, galvanic cell, which is a voltaic cell using a spontaneous chemical reaction to generate electricity, and I mentioned two things here. So, one reagent must oxidize and second one must get reduced, and the two should not be in contact. So, we talked about a situation where the most classic situation of Daniell cell, where we talked about the zinc and the copper electrode, where zinc getting oxidized and copper receiving those electrons generated by the zinc, and they are being separated in two different compartments, zinc in zinc sulfate and copper in copper sulfate, so on and so forth. Then we talked about a situation where we had a common electrolyte, which is cadmium chloride, and we had a cadmium electrode and a silver chloride AgCl electrode, which is essentially on a Ag, you have the AgCl coating, where oxidation occurs at cadmium electrode. So, cadmium moves into the aqueous medium as Cd2 plus, and the electrons which are left behind are forced to travel and being received by the AgCl electrode, because chloride from the AgCl electrode diffuses into the cadmium chloride solution, and so there is a dearth of electrons there. Those electrons travel all the way from cadmium electrode to the AgCl electrode, and there is a deposition of the silver on the AgCl electrode, right. And in order to drive this reaction, which is a spontaneous reaction, the delta G is minus 150 kilojoule per mole of cadmium getting consumed. And we calculate the voltage, what you will be observing, if you remember it. So, we talked about delta G is equal to NFE, remember the formula what we discussed in the very early 3 classes. So, delta G is equal to NFE, where minus delta G is equal to NFE. So, in this situation it was minus delta G, the value of delta G was minus 150 kilojoule per mole. So, essentially minus minus makes it plus. So, delta G value becomes 150 kilojoule per mole on the left hand side is equal to NFE, where N we considered as the cadmium solid becoming Cd2 plus into the aqueous plus 2 electron. So, we considered those 2 electron as your 2 moles of electron. So, your N becomes moles of electron. So, 2 moles of electron multiplied by the Faraday's constant. Okay, if you remember the Faraday's constant, the amount of charge on an electron multiplied by the Avogadro's number, that is what is the Faraday's constant. So, you multiply the Faraday's constant, you are left with E. So, 150 kilojoule per mole divided by N, which is 2, F, which is Faraday's constant, and 150 kilojoules. So you convert that into joule multiplying by 10 to the power 3, and the value what he was getting was around, I think, 0.77 or something. If we just do, this was the value which you obtained. Then we talked about a third case scenario where we talked about a silver electrode and a cadmium electrode. No more silver chloride. Okay, remember, silver electrode and a cadmium electrode, and we dissolved them in two different electrolytes, AgNO3 and CdNO3, cadmium nitrate and AgNO3 and CdNO3 too. Okay. Now here is a situation where we realize that there won't be any flow of electron per se, because what will happen, Ag, which is as the chloride is moving out into it, as the chloride will be moving out into it, the net reaction is a spontaneous, but little current will flow through the circuit, because Ag2 plus, so this is not chloride, I am just slight mistake, okay, Ag2 plus is not forced to be reduced at the Ag electrode, because the Ag plus is not forced to be reduced at the Ag electrode, whereas aqueous Ag plus can react directly to the cadmium surface or cadmium solid surface of the cadmium, giving the same net reaction with no flow of electron through the external circuit. So this was a very tricky situation. So there won't be any effective work. Now that is the point where we talked about we are introducing the salt bridge. So we are into lecture 6. So we are into week 2, okay, and for week 2 this is lecture 1, if I have to put it like this, week 2 lecture 1, okay. Now I built a different kind of cell today, where we will be talking about the salt bridge, the concept of salt bridge, and why there is a need for salt bridge. Need for salt bridge. Let's draw the situation where we did not get any network done. So here you have now we have two different beakers coming through. So you have the cadmium, we have the voltmeter sitting here or potentiometer sitting here, we have a silver electrode here, Ag, we have cadmium electrode here, and the solution it is dissolved in is cadmium nitrate, CdNO3 which is in the aqueous condition, whereas Ag is kept in AgNO3, so which is also aqueous, okay. Now this is your anode where the oxidation is happening, whereas Cd solid moving to Cd2 plus aqueous plus 2 electron. So this is one side of the reaction. The other side of the reaction is at the cathode, where you have 2 Ag plus in the aqueous plus 2 electrons 2 Ag solid. Okay. And if you remember, this Ag which is coming out from the Ag electrode out here, from this Ag electrode, this was the one which was migrating, that Ag2 plus was migrating on the surface of the cadmium and was consuming the electron and was becoming Ag solid and getting deposited on cadmium. You can use this for electroplating. You can coat a cadmium with silver on top of it like that. Okay. So, that was the reason why there was no external flow of electron, and that is where we talked about that we will be introducing the concept of salt bridge. Now, we will be introducing the concept, the basic fundamental of salt bridge. So, here we have a salt bridge now. What is a salt bridge and what is its role? Okay. Now, this salt bridge is a very interesting concept, and before I get into the salt bridge, we talk about, we can separate the reactant into two half cells. Okay. We have separated the reaction or the reactants, you can say, in this case, into two half cells. So, here we are introducing the concept of the half cells. So, please be very careful, this will come very handy, the concept of half cells. If we connect the two halves with now here we are introducing the fundamental of salt bridge. With the salt bridge, as we have shown in the figure here, this is your salt bridge. Okay. This is the salt bridge we are talking about, and we will talk about that what you are filling the salt bridge with. Okay. Salt bridge, what is the salt bridge? Now, we are defining the salt bridge. The salt bridge is a U-shaped tube filled with a gel. So, here is the gel containing a very high concentration of KNO3. So, mind it, this will change according to the cell type, KNO3 or other electrolyte that does not affect the cell reactants or the cell reaction, that does not affect the cell reaction. The end of the bridge. So, we are talking about these parts. Okay. These are the ends we are talking about. These are filled with porous material. End of the bridge are porous glass disc that allows ions to diffuse but minimize mixing of solutions inside and outside the bridge. So, it will not allow any further mixing. So, when a galvanic cell is operating, then potassium from, so I haven't introduced this, I will complete the drawing. Potassium from the bridge migrates to the cathode chamber compartment, and a small amount of NO3 minus migrates from the cathode to the salt bridge, cathode into the bridge. Now, let us see the picture, revisit the picture, what is happening. So, now here it is filled with potassium. Okay. So, let us draw it, that will make more sense. Okay. So, you are having a salt bridge which has lot of potassium salt in it. Okay. Out here what is happening at the cathode side, which is this side. So, there is a movement of some of the potassium ions coming onto this side. Okay. So, from here some of the potassiums are moving into this side, whereas some of the NO3 minus is moving out there. Okay. So, this is the small amount of movement of ion which are happening somewhere out here. It does not proceed further. This is where some of these potassiums are moving onto the cathode side. On the contrary, if you look at the anode side, something very interesting is happening. So, as the cathode is pulling out some of the positive charges in order to maintain. So, why it is happening? Because out here what is happening, if you look at it, this Ag plus is getting reduced by the electrons which are coming from the cadmium side. So, there is a dearth of some of the positive charges out here. So, just you have to imagine what is happening on this side. So, out here on this side of the story, there is a dearth of positive charges. Those positive charges, the dearth is being, so in order to maintain that potential difference, there is some positive charges in the form of potassium ions which are positively charged, they are moving, percolating into this side, little bit, not a whole lot of migration happens. Okay. On the contrary, if you look at the cadmium side, which is the anode side, what is happening? On the cadmium side, there is an excess of cadmium which is getting into the solution. Okay. Now, this excess cadmium which is Cd2 plus. Now, because there is a dearth of positive charges, because some of the potassiums are coming here, some of these cadmiums get into it, Cd2 plus from the anode chamber move slightly into the cathode chamber, and in return some of those NO3 which became excess here moves out here. So, on the cathode chamber, if you look at it, the negatively charged ions, okay, and ions, they migrated onto the there is a small amount of migration which took place into the salt bridge, whereas positively charged ions from the salt bridge, potassium ions, they slightly migrated to the cathode side. On the contrary, the positively charged ions from the anode side move slightly inside the salt bridge, which is your cadmium 2 plus, whereas some of the negatively charged ions NO3 minus from the salt bridge migrated into the anode side. So, what are the consequences of this kind of movement? That is very important for you to understand. Okay. Now, if we go back where cathode into the bridge. Okay. So, this part is very important, the ion migration. Why this ionic migration is essential? Ion migration offsets the charge buildup that would otherwise occur as electrons flow into the silver or the Ag electrode, because you are realizing that there will be a huge amount of charge offsets which will be happening, because there will be a lot of electrons which are traveling out here, and there will be a movement of the Ag2 plus on the Ag electrode to get reduced, and there will be a dearth of positive charges in the solution, which is being compensated by those positive charges in the form of potassium plus, which slightly migrates from the salt bridge. So, it is kind of doing a balancing act in order to maintain the potential difference across the two electrodes. This part, this concept has to be clarified. And the next, what is happening out here, if I come back out here, on the other hand, the migration of ions out of the bridge is greater. So, here let us highlight this part. The migration of ions out of the bridge is greater than this, keep in mind, than the migration of ions into the bridge, than the migration of ions into the bridge, or the salt bridge here, of course, into the salt bridge, because salt concentration in the bridge is much higher than the salt concentration in the half cell. So, that kinds of tells you that why there will be more diffusion from the salt bridge as compared to the into the salt bridge. Okay. At the left side of the bridge, which is now we are talking about the anode side, NO3 minus migrates into the anode, compartment. We have already mentioned it, I am just putting it down into the anode compartment, and a little CD2 plus migrates into the bridge to prevent build-up of positive charges on the anodic side. Okay. So, thus in order to prepare a salt bridge, what you have to do, this is a practical side of it, what I am going to discuss now. In order to prepare a salt bridge for a reaction that, so you have to be very careful that these reactions should not, these kind of salt bridge should not affect the reaction on the half cells. Instead, they are only used to maintain an offset. Okay. As we will proceed further in the practical application, you will realize why these are so significant. Now, coming back to the salt bridge. Okay. For the reaction that do not involve silver or other species that react with chloride, the salt bridge usually contain KCl electrolyte, and a typical salt bridge is prepared by 3 gram of agar with 30 gram of KCl in water. You can prepare this till you obtain a clear solution, okay? And the solution is poured into a U tube to allow it to gel. So, you prepare the solution and pour this solution into the U tube till it becomes a gel. So, this is how you prepare these kind of salt bridges, what we talked about. And talking about the line notation, here single line showing the phase boundary and the double line showing the salt bridge. So, the cell in this case cadmium solid CdCl, which is the aqueous. So, this is the phase boundary between cadmium and cadmium chloride, and this is that electrode what we talked about earlier, where you do not have any separation. You have the AgCl solid, Ag solid. Okay. So, this is where with a single electrolyte we could achieve it. So, this is essentially the case of, this is the case. Now, if we talk about this current reaction, then this will be Cd solid, cadmium solid, Cd NO3 2 aqueous. Now, here is the salt bridge AgNO3. Let us have the line notation for it, where you have cadmium solid, so cadmium nitrate. So, this is the first phase boundary we are showing, which is cadmium nitrate is the electrolyte in it, in which it is. So, you have the cadmium electrode and in contact with cadmium nitride. So, this is the phase boundary which is shown by this one line, and then you have this, pick up another color. So, you have this salt bridge which is shown here. So, you have AgNO3, which is your aqueous phase AgNO3 with the phased Ag solid. So, this is essentially the reaction what we just now discussed, how you are going to write in the notation of line notation. This is what this reaction should be written. Again, I am rewriting it: cadmium solid, Cd NO3 2, which is your aqueous, double line which is your essentially your salt bridge, followed by your AgNO3 which is aqueous, which is this one, with a phase boundary out here, you are showing Ag solid. So, that brings us to a situation where we have covered all the different aspects of the galvanic cell. That gives you a compact idea how one can force the electron to flow into the external circuit, how you have these salt bridges which are compensating for much of this movement and the mass movement of the ions, how they are helping you to create an offset because of the charge buildup, positive charge or negative charge buildup. So, I will request you these last 2 lectures, 3 lectures are extremely important. Please go through them, listen to them very carefully. If you have doubt, please put them up in the forum. I tried to cover as much as I can by spreading 3 classes on galvanic cells, because I felt that this is very important that this clarity of thought comes in your mind, and I am thankful to the TA who pointed out this point. So, from here we will move on to the standard potential and the Nernst equation, and we are slightly lagging behind, but do not worry, we will cover it up. Okay. Thank you.